Hello. My name is Sam. I will be replacing Professor Boyd for this lecture as he is in Rochester at the conference currently held there. This is the 6th class of the semester. So this class will be about the intensity-dependent refractive index. So specifically, we'll be talking about the nature of this intensity-dependent refractive index, giving you some intuition about it. We'll talk about how it is related to chi3, and then, if we have time, we will finish a particular case of the intensity-dependent refractive index and the effect of chi3 by talking about the molecular orientation effects. So this is all, if I'm not mistaken, this is all in the chapter 4 of the book, and most of the time Bob's lectures follow the book. I'm sure you've noticed. So if you have questions, you can refer there or ask me, but the book has higher authority than me. Okay, so So as the name implies, some material have this property that the refractive index, the value of the refractive index, changes depending on the intensity of the light that travels through it. One of the most early definition, or I should say, the way of representing this thought is this way. So you have the refractive index that is given by the usual linear refractive index plus some N2 parameter here that I will explain soon, times the time average of the square of the time varying electric field. So you're already familiar with this notation, I'm sure. Basically this is the N2 with a bar over it is a rate of change of the refractive index when you have a certain time average refractive index. But more recently, and for practical reasons, there was another way of expressing this alternative way by going to directly to the intensity. So you have the linear refractive index plus another parameter that is basically the same thing up to some factor and times the intensity. And so we all know that the intensity is simply given by the linear refractive index NO times speed of light over 2 pi times E omega square. This is the usual definition of the intensity. So we can find that, because they must be, those two expressions must be equivalent, one can find that N2 is equal to N2 bar divided by N naught C epsilon naught. So it is more practical to use intensity simply because this is the quantity we use in the laboratory, right? Okay, let me take a step back then. Yes?
I want to find out where this relation comes from, because it's just a definition, or no, there is some reason behind it to expressing refraction index in terms of ordinary refraction index plus something times the intensity, or no, it's just as definition, or no, there is some reason behind it.
It is a definition. It is really it is a definition. And this definition arises from the property of chi3, as we'll see in a second. So, so let's answer your question and look at how this whole N2 thing is related to chi3. So this is all related to chi3. Third order nonlinear susceptibility. So again, you know from the previous chapters that the nonlinear polarization is simply given by, now I'm switching sides, I hope I'm making things, not hiding the board. Is it better this way? Yeah, okay, very good. So this is given simply by 3 times chi3 e omega e of omega. So using the convenient notation with the frequencies, we can write this expression. Let me remind you that this is describing a process where the refractive index is being modified by a beam of light propagating in a nonlinear medium. So now I'm giving you a clue as to why there's this factor 3 here. Do you have an idea why there's this factor 3 appearing?
The degeneracy factor?
Yeah, this is just the degeneracy factor appearing. So chi3 here corresponds to the specific chi3 where, well, expanded omega plus omega minus omega. So you have this degeneracy, like those permutation between all the different signs that appear in the chi3 process. And so you can write the total. So those two contributions, linear and nonlinear contributions to the nonlinear to the polarization. Sorry, p dot of omega is given by chi1 e of omega plus 3 chi3 e of omega square e of omega, right? And I can write it in such a way that, factoring out this electric field here, such that I have this chi effective e to omega, where chi effective is given by chi1 plus 3 chi3 times the electric field. Okay, so we know from Maxwell's equation that the refractive index square is equal simply to the dielectric constant, and this is equal to 1 plus chi effective. Simply, right? And so one can write n naught plus n2, plus 2 and 2, basically just using this definition here. E. So this is square. So this is, I'm just replacing the refractive index, and then I'll be replacing this, also this expression by this definition here. This is simply 1 plus chi1 plus 3 chi3 . Okay, so I can make an approximation in the form of keeping only the terms that are so I'll be keeping only the terms, right? So I can write it in this way. So here really again separating two different contributions. So it is kind of clear, right, that you see those two guys appearing. And so, yeah, so n naught is equal to 1 plus chi1, and n2 is equal to 3 chi3 divided by 4 n naught. Right, and again, using intensity instead, I can write that n2 is equal to 3, 4 n naught square epsilon 0 c. This is times chi3. Okay, so really one can see that well, it is rather clear that you can achieve a higher intensity-dependent refractive index when you have a higher chi3, and at the same time you have a lower intensity-dependent refractive index when you have a higher n naught. So those are two things that must be considered when you want to be looking into this kind of material, or when you want to use these properties. So simply put, when you have a certain beam that enters a medium, this medium is dependent, has a intensity-dependent refractive index at the output. You will have the same beam of light that you would have at the input, but there is a new phase to it. And so if you wanted, you could take this guy, or you could make an interference between this guy, and determine the value of phi, and by measuring this value of phi, you could extract what is the value of chi3. So you've had all those chapters, just finish the thought, you've had all those chapters beforehand where chi3 was, 81 terms you needed to go through, and like chapter 3 is kind of intense, right? And then you can just go to the lab, do a measurement like that, and you could have a measurement of chi3 for this specific case. Yes?
Where that a phase comes from?
So in general, the phase acquired by a optical field in a medium is given by, and you write phi is equal. There are countless ways to write that. You can write it that the wave vector times the length of the medium. Right? And so k is n times, this is the refractive index, times omega over c times L. So you recover the n basically, right? If there was no medium there would be no phase shift, and then you make them interfere and there is a phase shift. You can measure this phase shift, thus retrieve the n, or actually what you are retrieving here is directly n2, yeah. You're directly retrieving the n2. Basically the difference in the refractive index, right? There's another way to measure the refractive index that depends on intensity. This is called the weak wave retardation. So it's the very similar principle. You have a strong beam that I will call E, it's E of omega, and I have a weak beam that has a slightly different frequency for reasons that relate to the nonlinear polarization, and you have this intensity-dependent refractive index. So what you have at the output is a phase shift for the weak wave. This phase shift, E omega, is expressed in the same manner that was expressed beforehand. And if I write the expression explicitly, I find that the nonlinear polarization is given by, for the frequency omega prime, is given by 6 chi3. Omega prime is equal to minus omega plus omega prime, and then there is the electric field, E of omega square, and then E omega prime. Note that there's a 6 here for the same reasons earlier that we had a factor of 3 here, but you all know that. And in this case, you find that the N2 for the weak beam, let me denote it this way, N2 is given by, oops, and now there's a mistake in the notation, is given by chi3, let me write down, yeah, there you go. There was a mistake here. And so, yeah, you find that N2 is twice as large as the N2 you would get when you have this only only one beam propagating in the medium. I think sometimes it was questions in assignments in the past. I think Bob was asking, or Professor Boyd was asking for a intuitive explanation as to why that was the case. So why this factor 2 was arising. And so just in case it's in the assignment, I will not go there, but I think this is something that you can find interesting to answer in general. Yep. Yeah, so this is all stuff you know already. That's right. Oh, this is also called, by the way, for your knowledge, this is also called the pump probe measurement. It might be called like that in the book. And so here in the notes I have, a probe wave is slowed down more than the pump wave in this medium by a factor that is twice as large, right? This N2 is twice as large. Okay, so now that we've covered this material, I will try to give you a flavor of the orders of magnitude of those values that we're talking about. So mind if I erase this part? All right. So there's basically many mechanisms that can lead to this intensity-dependent refractive index. So such mechanisms, yeah. So one mechanism that you're familiar with is electronic polarization. So this is the one that we often talk about. You have those energy levels. They relate really to the energy level of the electrons in the atom. And so for electronic polarization, you will find an N2 in the units of meter square divided by watts. The units agree with the definition that we gave earlier. We'll find that, and sorry. Whoop. Okay. This is 10 to the minus 20. And so this gives you a flavor that, for this kind of processes, this is typical values. It's not for all materials, it's just typical values that you will find for most materials. Just to give you this idea that you will need to have a pretty high intensity. You need to have a pretty high intensity in order to get a a sizable change in the refractive index. So another mechanism is the molecular orientation. Molecular orientation is, well, you have to think of some molecules that have elongated shapes or some complicated shapes, but just for the argument, it's considered just elongated shapes, and these molecules will tend to align with the electric field. And this alignment, or rather how the medium, the response of the medium, depending on this alignment of the molecules, will give a intensity-dependent refractive index. So here, 10 to the minus 18. Another one is electrostriction. Electrostriction. Fancy name just to say that in some materials there's this effect that the medium tends to become more dense when there is a higher field or intensity of the field, right? So again, this is part of the later parts of this chapter, but this is really just a rough definition. And so the order of magnitude is again 10 to the minus 18. Then you have saturated absorption. Pretty self-explanatory. Thermal effects. And photorefractive effect that is not really relevant for the purpose of this class. And so here 10 to the minus 14 and 10 to the minus 10. But all those mechanisms are accompanied with, they all have a typical response time. Typical response time. I will call this the response time. So here in seconds. So 10 to the minus 15, 10 to the minus 12, 10 to the minus 9. So here, try to make it clear. 10 to the minus 8, and 10 to the minus 1. So it is pretty clear, or one can deduce from this chart, that if you want to have a very high refractive index due to the intensity, you will find that the response time is really low. Why are we talking about the response time is because, of course, some of us are, some of us want to be useful eventually by using the nonlinear optical effects, and response time are really important whenever you deal with telecommunication, of course. So one possible application of nonlinear optics that has been really driving the field, not to make a pun, is switching. You've heard of switching. I think Bob has mentioned it before. So when you want to do switching useful for the telecom industry, we are talking about gigahertz rate, right? And so when you are using thermal effects, I'm not sure you can achieve this kind of rates. So we are looking at this kind of trade-off between the amplitude of the nonlinear index or nonlinear refractive index and the response time. So there's this trade-off, and typically this is the kind of values you will find, but some people are magicians and are able to take advantage of the properties of materials to engineer these kind of values. This is beyond the scope of this class. Okay, so far so good. Are there questions about N2? Yeah, let me just say also that in general, for the purpose of vocabulary, this is often called delta n, or yeah, the change in refractive index. This is often called this way. So N2 does not have N2 has, as you've seen, N2 has units, right? Whereas delta n would be a unitless value, or rather it would have the same dimensionality as the refractive index, right? Okay, so are there questions?
Maybe a stupid question. So why don't we have chi2 here?
Because usually in chi2 processes, the wave does not affect itself, right? So let me answer your question by looking at this equation here, over here. Is there a possibility that the wave omega, the wave at the frequency omega, will affect the wave at frequency omega through the polarization?
One DC field and omega, sorry.
Well, how do you define the DC field?
Omega equals 0.
Yeah, well, I mean, you're playing with the words, right? Did I understand, did I answer your question?
I'm not quite sure.
So here we have this combination of waves. Omega plus omega minus omega is equal to omega. Now in a chi2 process, you're only allowed to have two waves interacting here.
Yeah, got it.
I will give you $5 if you find a way. Actually, you will probably become much more rich if you find a way to. Anyway, okay. So if there's no more questions, I will erase this, and maybe while I erase this, you can think of very clever questions about this. So I don't know if Bob has mentioned it before, but there is this very interesting part here that no one so far among you has noticed, or rather that you have noticed, but you're way smarter than me, so you think it's trivial. But one way to have a very large N2 would be to have a linear refractive index that is really, really low. So it is not forbidden in optics to have a refractive index that is close to 0. And so some materials, say for instance metals, have this very bad property of not propagating light through them. But it is possible, if you look at the optical properties of metals, you will find that they have very low refractive indices. And so in principle, they can have very large N2s. So this is a field of research that is very active at the moment, trying to use those properties to enhance the nonlinear refractive index. Oops. I erased everything now.
I know. In the refractive index from a higher order nonlinears, like chi5 or chi7.
Absolutely.
But
yeah.
I'm assuming they're so small.
That's right.
That's
right. Yeah, here we assume that it was only from chi2, okay. Chi3, processes. So now we'll be talking about isotropic medium, and in particular properties of chi3.
Question before you go further. Pockle cells.
Oui, Pockle cells, yes.
Yes. So isn't that the change of refractive index with chi2?
It is not the same thing, is it? Pockle cells are based on, and I don't use Pockle cells often, but it is not based on the same thing, right? It's not a nonlinear effect in this sense. It is a linear effect based, if I'm not mistaken, on the orientation of, is it like the orientation, you apply a voltage.
You apply a DC field.
That's right.
Which
Yeah.
polarization.
That's right. So it's all about birefringence. And birefringence is linear.
So changing the birefringence is changing the refractive index.
Yes, but it is not the same thing. Birefringence is based on, and it's funny that I just wrote this, but birefringence arises from the anisotropy of the material, and it's not the nonlinearity of the susceptibility.
But it comes from the voltage you apply. So,
Yeah, so about the voltage, I will not try to answer your question in details, but birefringence is really a linear effect. Okay, so we want to talk about the tensor nature of chi3. Chi3, as we've just seen, it's so simple, right? You can measure it, but of course you cannot measure, like, we've just been talking about one element of this four-dimensional tensor. Sorry? So how many elements does chi3 have? 81 elements. I think I mentioned it already, right? Chi3 has 81 elements. So chi3 is often, you can write it this way, right? I, J, K, L. I, J, K, L are all the Cartesian coordinates, and so you can easily deduce that there is 3 to the 4 elements in chi3. So for keeping things general, we will consider the case where you have such a process such that all the frequencies are different. All right? I didn't talk about isotropic material. Isotropic medium means that the properties of the medium are independent on the orientation, on the spatial orientation. Okay, all said. So one can find, because of this isotropy, one can find that chi 1, 1, 1, 1, 1, 1, 1 is equal to chi 2, 2, 2, 2 is equal to chi 3, 3, 3, 3, which makes sense because it's isotropic. If I'm looking at all the polarization that is induced in X or in Y or in Z, it shouldn't change when I change the orientation of the crystal or the material or the medium. And by using similar arguments, one can find, this is horrible, okay. One can find that, there's a bunch of 2, 2, 3, 3 other symmetries like that. And likewise, 2, 1, 2, 1, 3, 1, 1, 3, 1, 3 is equal to, well, it's all in the book. 2, 3, 2, 3, 2, 1, 2, 1, 3, 1, 3, 1, 3, 2, 3, 2. And then I have 1, 2, 2, 1 is equal to 1, 3, 3, 1 is equal to chi 2, 1, 1, 2, etc. Using the same kind of symmetries, or like changing the numbers accordingly. So you would find that there's only 4 non-vanishing terms in the tensor. This one, this one, this one, and this one. Only 4 non-vanishing terms. But wait, I didn't talk about a bunch of other terms. I didn't talk about 1, 2, 2, 2, for instance. What about this guy? Well, why do I say it vanishes? I will say, well, I said it vanishes because here I'm talking about the one here, and I'm talking about the induced polarization due to the 3 other fields. And in an isotropic medium, it does not make sense that I have all the other fields in one other coordinate inducing a polarization in another Cartesian coordinates. So that's why by inspection those guys vanish, right? So every time there's an odd number of a Cartesian coordinate that appears in the indices of chi3 elements, well, this element vanishes in an isotropic medium. Okay, so I'm left with only with those four elements of components of chi3. And one can find also that these four elements are not independent from each other. So you will find that chi 1, 1, 2, 2 plus chi 1, 2, 1, 2 plus chi 1, 2, 2, 1. And this is based again on the isotropy of the medium. I think it's a problem left in the exercises of the book that if you take a medium and you make it rotate 45 degrees, you can find this expression based on this kind of, based on the conservation of the properties, basically, upon changing the orientation of the crystal. This is isotropy. Okay, so now that we've considered this very general case with those frequencies, we will jump to a more specific case where the plus is here. Yeah, the specific case where we have this kind of interaction. So, yeah, for this kind of interaction, we will find that, it has some consequence here on one of those components here, that chi 1, 1, 2, 2 is equal to chi 1, 2, 1, 2, and this is a result again of the permutation symmetry, intrinsic permutation symmetry, right, that we have been using so far. So for this case, we find that for the coordinate I, the component of the polarization is given by 3 epsilon 0 chi 3 of I j k l omega is equal to omega plus omega minus omega. Now you find ej, the usual stuff, ek omega and el of omega, and this is star. And so one will find, based on this property, this condition, relation that we found, this equation, relation that we found as well, we will find that P can be written as 6 epsilon naught chi 1, 1, 2, 2. You will find this expression. So yeah, you see that now we are left with only two independent elements in the chi3 tensor. We're left only 2 elements. That's a pretty nice achievement based on the earlier number that we had here. So there's a notation, a convenient notation that was introduced, and we're just going to use it. So let me just introduce it. There's this A parameter that corresponds to chi 1, 1, 2, 2, and the B parameter that corresponds to 6 chi 1, 2, 2, 1. So I can write P as epsilon naught A E times E star E plus 1/2 epsilon naught B E. Am I writing large enough?
Yes.
Star. And so this is a, well, you could already see it from here, but with the notation here, we make it obvious that there is an interesting difference between the two terms. So when you consider that light can have different polarizations, so for instance, linear polarization, if you take the complex conjugate of light that is linearly polarized, well, you will get the same linear polarization. It's not really interesting. It doesn't change anything here. But when you consider a case where the fields of light have circular polarization, then it matters. Because when you have left circularly polarized light and you take the complex conjugate of it, you get right circularly polarized light. And so they will have different contributions here based on the circular helicity of the definition based on the helicity of the polarization. So one can think of it. So there's this kind of nice, I'm trying just to give you an intuition of what's going on. This intuition is not perfect. It's just giving you a picture of what's going on. So it's often really useful to consider this, those nonlinear processes as those arrows and energy levels, right? So for instance, if you have E star and E here, and the last one will be this. So the first contribution corresponds to this kind of physical process, whereas here you can think of it as E, so up, and down, and down. So the last one will be the down, just as usual when you write the driving fields, of this kind of process.
I don't quite understand this figure.
I'm sorry?
I haven't quite understood what do you mean by up, down?
Well, so far in the semester, when you've been talking about Chi2 processes or Chi3 processes, you will notice that when you have the electric field like that, or the electric field with a star, usually it corresponds to this and something corresponds to this, right? So this is just what I'm picturing here. You have EE here, and this is the third field going down. Yes?
In your equations for the polarization on the right side of the board, what happened to the terms of the form like chi 1, 1, 1, 1? Like, do those, so do terms like those disappear?
What happened to chi 1, 1, 1? I got rid of it here, I think. Yeah.
Oh, okay. So
I used this relation, and then, that's where it went. So I used this relation to replace by all those guys, and then there's this guy here. That's right. Okay, so there is this story that Bob likes to tell about this this picture here. He's saying, just imagine that you have an atomic, some two-level atom or some atomic transition that we're considering. And this is an S level, and this is an S level, if you're familiar with the orbital type of orbitals. Well, here there should be conservation. There should be conservation of the angular momentum. And so if you come with right-hand circular light, and you come in with right-hand circular light, Well, the complex field, the conjugate field will be left-hand circular light and left-hand circular light. So it just means that in this whole process, you should be careful into keeping the orbital, the angular momentum conserved, whereas here it didn't really matter, right? So this is like two different cases. Okay, so I mean, it will become a bit more clear, hopefully, when we go through with the lecture. But basically what we are trying to figure out is what happens to the light when it enters a nonlinear medium. What happens to what happens to it? And one thing that we will find is that there might be some kind of rotation of the polarization. We're going there. I do not need to talk about this. And so, of course, the next section is called propagation through isotropic nonlinear medium. So I will start here. Propagation through isotropic nonlinear media. And so the question that we are trying to answer using this equation is if I enter with an arbitrary polarization, so here I've been drawing elliptical polarization, which is arbitrary. So if I'm entering with an elliptically arbitrary polarization of light into this chi3 medium, isotropic, what do I get at the input? Okay, so let's start off with nonlinear polarization. Only the nonlinear polarization, we find that it is given by, as we found earlier, it is given by this equation. And so here we need to use a bit of abstraction. We'll be thinking of we will be decomposing all the linear polarizations into circular polarization and be working in this new basis of circular polarization. It will help us to highlight the process or what happens to this input polarization. Yes?
I got a little confused with the figure. So if you have two right hand circular, I mean the circular polarized light. So you have, for example, you have m equal to 0 and m equal to 1 and 2, but you cannot reach the S states again because for S state m can only equals to 0. Is that right? I mean, if you have a right hand side and a right hand side, should that be R, L, and
Okay, so in general, S states possess no angular momentum, right? Or rather, if I want to come back to the S state, there should be no angular momentum in the light that is composing it. So this is just a thought following this. This is just a picture following this thought. I mean, don't overthink it. Where we're going is really more trying to answer this question. I'm really just trying to, I was just trying to give you an idea of why those two things were different, but it will appear also in this treatment here why those two processes are so different. Okay, so we will need to use a new basis. So we'll write the electric field as a contribution plus and a contribution minus. Same thing for P. So those are our new basis vectors. You're all familiar with the concept of circular polarization. So if I make the summation of linearly polarized light in X and linearly polarized light in Y, and I introduce a phase of I, this I, between them, I will end up with left-hand circular polarization, or minus I, it will be right-hand circular polarization. So just here, I'm really just separating any polarization into a basis E plus, or left-hand circular, and E minus, and those two base vectors. So those vectors, yeah, sigma plus and sigma minus have properties, and just to make things thorough, we'll write down those properties. So the complex conjugate is given by minus or plus first. Dot product. So this is given by, I will let you do the algebra. This gives us 0. And now let's consider dot product, but with the other handedness, it gives 1. And now let's consider the dot product with the complex conjugate. Oops, this is plus or minus. And now this is the complex conjugate. It's equal to 1. Yep. So we can find from these properties that we have those fields, those factors that were appearing, E dot E star is equal to product, cross products, and we find that it is equal to E plus E minus square. And likewise, dot product with itself is equal to 2E plus E minus. And then we find, by substituting those factors in the equation for the nonlinear polarization, we find that this is equal to epsilon naught A E plus square plus E minus square E plus epsilon naught B E plus E minus E star. So if you use the definition we had earlier with the same kind of change of basis, but for the polarization, you will find that P plus is equal to epsilon naught A E plus square E plus epsilon naught A plus B E minus E plus, and likewise P minus is equal to epsilon naught A E minus square E minus plus epsilon naught A plus B E plus square E minus. So, why did he write that down? So again, we just made use of this substitution, and eventually we'll reach the conclusion of this part. Don't worry. May I erase that part? Yes. Oh yeah, and just finishing that thought, I can now define a nonlinear refractive index for each of these guys. I said index, nonlinear susceptibility, sorry, such that P plus or minus is equal to chi plus or minus NL E plus or minus, and chi plus or minus is equal to A. This is just algebra, right? All right. So now what we want to do is to solve the propagation problem. What happens to an input polarization of light when I send it into this nonlinear medium? I need to solve the differential equation that describes the propagation, which is given by this is from chapter 2, right? You've seen that before. So you can decompose this whole equation into those plus and minus bases that we've introduced before. And you will find that you have this equation, plus or minus z and t is equal to epsilon plus or minus. And now I define this epsilon effective c square plus or minus zt dt square, where epsilon effective, epsilon plus or minus effective is simply equal to epsilon 1 plus chi plus or minus NL, and epsilon 1, just as a reminder, is simply the linear refractive index squared. Okay, so we see that the wave corresponding to this polarization and to this polarization, or for plus or and minus polarization, they each have their own propagation equation. They each have their own propagation equation with the following effective index that is given by E plus or minus effective. So we just found, and this is not too surprising, but at the same time this is a bit counterintuitive, that we have a refractive index that corresponds for the plus polarization and refractive index corresponds to the minus polarization. So, since n plus or minus square is given by n naught square plus chi plus or minus NL, and this is just from the definition of what a refractive index is. We have n naught plus. Now I introduce this definition that I used there, a e plus or minus squared plus a plus b e minus plus. And then I find I can spare you some lines, and you will find that n plus or minus, and now there's no square here, I can make this approximation. This is approximately equal to n naught plus 1 over 2 n naught squared a e plus or minus squared plus a plus b e minus or plus squared. Wait. Yeah, that's it. Yeah, that's it. So the left and right circular components have a different refractive index such that n plus minus n minus is equal to b 2 n naught e minus squared minus e plus squared. So this means that in general, since the plus polarization and the minus polarization propagate with a different refractive index, they have a different retardance while propagating through the medium, it means that at the output I will of course get in general I will get a different polarization. Now this is just an isotropic medium, right? All we had here is an isotropic medium that had some nonlinearity in it, and you find that an elliptical polarization will exit with a new elliptical polarization at the output. But wait, what happens when I come in with a circular polarization? When I come in with a circular polarization, it means that in any linear bases that I use, I have equal wait, if I come in with a linear polarization, if I come in with a linear polarization, it means that in the circular basis, I have the exact same amplitude in the minus and in the plus. This is basically the definition of linear polarization in a sense. So this guy minus this guy would be equal to 0. So if I come in with a linear polarization, I will end up with the same linear polarization. There is just no change in polarization. If I come in with a circular polarization, I will find that there is what you get at the exit is just the same circular polarization, because it will experience its own retardance, right? But not relative to the other retardance. Make sense? So we have those two eigen polarizations, so linear and circular polarizations, that will not be affected by this propagation in the medium. So one can express this explicitly by writing that the field at the distance z in the crystal in the medium will be given by a plus e I delta n omega z over 2c plus a minus e to the minus I delta n omega z over 2c and minus, and this whole thing is multiplied by a e to the I over 2 n plus n minus omega z over c. let us introduce this angle theta, so that this electric field is now given by A plus e to the I theta plus A minus e to the minus I theta. This is just more compact, and I find e to the I k m z, and yeah. I feel like there's something missing from in this factor from the notes I have, but this is just simple algebra, so I mean, just for this part, I don't know about this exactly this factor, but it's basically the same thing as here. So theta, if you look at this equation, you can really see that theta is exactly the angle to which the polarization ellipse changes. So coming back to what we had before, I come with a polarization, elliptical polarization at the input. I find that the output is the same ellipse, but really just rotated by some angle. Oh, sorry. By some angle theta. Wow, we have found that. So yeah. Let me look at the time. What time is it? 3:38. Okay. So at 4, we're going to take a break, by the way. So what else can I say about this? There are some other considerations. So I've already been talking about the eigenpolarizations. So I find, so something interesting is that is worth mentioning is that the difference in the refractive index depends only on the B, right? So I've been talking about the difference in the A and the B. I've been trying to give you, well, I more or less failed at giving you a picture of the difference between the two, but it's quite remarkable that the only contribution to the difference between those two polarizations is given by the B factor. I would love to give you more insights about this, but I could not. If you have more questions, of course, you can just ask Bob, but now you know the basic math and that relates to it. Just lacking some interpretation. Okay. We find that if you come in with linearly polarized light, you end up also with linearly polarized light. Now I'll erase that. It doesn't very determine the time. Yeah. Give me a second. Just double checking some equation. Okay, so if you come in with a, so how do we, so yeah, if you start off with this equation, n plus or minus, you can find that for linearly polarized light, there is no delta n, so delta n vanishes, but there is still a refractive index that is different from n naught. So now I'm just going to denote this change in refractive index as dn linear. This dn linear is given directly by 1 over 2 n naught a e square. Wait, no, this is not true. Dn linear is not given by that. It is given by, sorry about that, 1 over 2 n naught. It's the same thing. Oh, that's it. A plus 1 over 2 b e square. Okay, so it is, and maybe I did not go far enough into these. Oh yeah, so remember earlier on, right here, a bit earlier, we defined what A and B were, and based on the definition of A and B, there is this relation that 1 plus A plus 1 half of B is equal to 6 chi 1 1 2 2 plus 3 1 2 2 1 is equal to 3 chi 1 1 1 1. And this kind of relation, just to make it short, this kind of relation, I would write it down. Dn circular is given by 2 n naught. And this is just a e square. So we find that even though we have established that circularly polarized light and linearly polarized light are eigen polarizations of this medium, of the propagation in this medium, we still find that they don't have the same refractive index. We find that linearly polarized light and circularly polarized light do not experience the same refractive index. And the ratio between the two is given by this expression, 1 plus b over 2a. Just a second. And it turns out that the ratio between the chi3 elements, the relation between the chi3 elements, which is reflected by the b and the a parameter, depends on the process we're talking about. So earlier, I've written down the different type of chi3 processes that have exhibit an intensity-dependent refractive index. Well, it turns out that this ratio is equal to 4 for molecular orientation, it is equal to 3/2 for non-resonant electronic transition, and 1 for electrostriction. So again, we found something interesting. We found that there was that this type of medium had certain properties that were not only depending on the polarization at the input, but also had very clear differences depending on the type of process that we are considering. Okay, so There was a question.
So we're saying for circularly polarized light, delta n vanishes. Is that what
Circularly polarized light, delta n.
is that what you
Yeah, delta n. Well, it's not really that delta n vanishes, right? It just means that.
I've been mishearing because I didn't see how it vanished. That's why I was confused. I think I just misheard.
That's right. It's not that it vanishes. It's really just that you don't have two. You don't have two. You don't have two. What's that? So let's put it this way. If this is equal to 0, you will have only n plus, and there's like n minus is irrelevant. Like there is no change in the overall propagation of the wave that you had at the input. Or rather, like here you can see that you'll have only the n plus here, and yeah, anyway. I don't know if that made sense.
No, yeah.
I would like to pinpoint exactly where, yeah.
So is that true for circular, whatever angle we rotate is the same?
Well, yeah, exactly. So the difference between, so there is an actual change in the refractive index. It just means that the polarization will not change. But I mean, the overall thing will rotate a bit, right? It will rotate a bit due to this, this guy. Yeah. It's not that the change of refractive index vanishes. It's really just that there is no change in the polarization because there is no counterpart that is experiencing another retardance, if that makes sense. Okay, so now we'll be talking about nonlinear effects. Nonlinear effects due to the orientation of molecules. And so the kind of medium we're talking about here is, for instance, organic liquids, which are made often of complicated molecules that can be like that have weird shapes, and often we can just module or rather simulate those shapes as being, I mentioned the Siger shape, or some other elongated shapes or whatnot. And we will find that this kind of molecules have a response to electric field that may result in changes in the refractive index. And this is what we will be looking at right now. What is the primary mechanism that you can think of that those molecules would change the refractive index? Well, rather, how do they react to the field, basically? They react to the field, basically they tend to align themselves with the field, right? You subject them to an electric field and they will tend to just change their orientation, right? And so as a, and just for the order of, I think I've told you earlier on, but the kind of time frame that we're talking about, response time, I think I mentioned it was on the order of the picosecond, right? Something like that. So this is the kind of response time that we're talking about. So in a, well, consider a, let me just draw it better, some kind of three-dimensional molecule like that. This has a symmetry axis like that, and you apply an electric field in this direction. Well, what you will find is that what you will find is that the polarization of this molecule will be in a direction that is not necessarily trivial, right? And here, let me just write. So this is the symmetry axis, and this is the induced dipole moment. I said polarization, but when we deal with microscopic molecules, we call it the dipole moment. So we find that the dipole moment is given by this expression, where this is the polarizability. The polarizability is a tensor times the electric field, and this is the tensorial nature of this polarizability is why the dipole moment is not oriented in the same direction as the electric field. All right. So it is not parallel to the electric field, and hence it will experience a torque that will be given by this expression. So P times the electric field. This is vectorial product. You are all familiar with these kind of equations, I'm sure. And so this torque will tend to align the molecule in the same direction as the electric field. So I can readily define some kind of a in this kind of molecules that has some kind of symmetry, right? If it was a spherical molecule, it would have the same. It would have only diagonal elements of the polarizability. But here, in this case, there is two elements in the polarizability. The first one is the one that is perpendicular to the symmetric axis, and the other one will be parallel to the symmetric axis. And from now on, I will define the angle between the symmetric axis and the electric field as theta. Just keep that in mind. Just give me a second, just making sure that I'm not yeah. Okay. Good. So, in the notes that Bob gave me, there's an equation, a random equation. You know, like he just wrote a random equation, not talking about it. I was like, am I supposed to write it down? Am I supposed to talk about it? And I'm pretty sure well, it seems that I should talk about it, but I have no idea what to say about it, really. And I cannot even find it in the book. I should have seen this in my preparation, but I overlooked it. So, yeah, I will probably not talk about it. In that case, it should be somewhere in the book then. Okay. Well, let me just write it down for just to be on the safe side. And so what is written right there is that chi1 is given by n. So I think what is written is that, you know, this is all microscopic effects. But if you look at the macroscopic effects, you will find you can retrieve the chi1, and by retrieving the chi1, you will find probably that it is given by n. N should be n should reflect the number, the density of molecules that you have in your liquid, and you will find it is given by 1/3 alpha parallel plus 2/3 alpha perpendicular. And I think that this relation is the consequence of the type of molecule that we have here, to be a property of this cigar-shaped molecule. And you will find also that chi3 is given by 2n divided by 45 for some reason. Yeah, I really apologize for that. N divided by kt. It doesn't seem that we will derive this. And so let me switch to another effect, or rather, starting from this, we'll talk about the Carr effect. Carr effect is again the same kind of effects we've been talking about. So the influence of a optical wave on itself. So this is the Carr effect. So everything we're talking about, the N2 and such, so that's Carr effect, by the way. So so I've given you this idea that when you apply a static electric field, you have this molecule that will tend to align itself with the electric field. But now we need to switch gear and think of oscillating electric field. So when you apply an oscillating electric field, there is two effects that are counteracting on the molecule. So the first one is the field that is oscillating, and the other one is thermal agitation of those molecules. So if you're familiar with your statistical physics, you know about the thermal agitation of those thermal vibrations of molecules, and that will randomize the molecular orientation. And this randomization needs to be taken into account to describe the response of those molecules. So the change in potential energy when you apply an electric field to such molecules is given by the U, where U is the energy, is equal to minus P times dE. This is valid also for static electric field, by the way. And it is given by minus P parallel dE parallel minus P perpendicular dE perpendicular. So we have decomposed E into its component, and of course, you know that P, well, you know, I mean, you can find, it is understood that the components of the polarizability are given by, or the dipole moment are given by the polarizability like that. And thus, U du, the change in potential energy is given by minus alpha parallel E parallel dE parallel minus alpha perpendicular E perpendicular dE perpendicular. Now you can integrate this to get the total change in the potential energy, which is minus 1/2 alpha parallel E parallel square plus alpha E perpendicular square. So as I mentioned, theta is the angle between the electric field and the symmetry, the axis of the molecule, and we can rewrite this equation as minus 1/2 alpha parallel E square cosine of theta, this is squared, plus alpha perpendicular E square sine square of theta. This is equal to minus 1/2 alpha perpendicular E square minus 1/2 E square cosine of theta, and there's a square somewhere. That's right. So far we have been assuming that the elements of alpha are positive. This is a normal assumption. Normal assumption for most anisotropic molecules. So this assumption implies that when you have the molecule oriented like that and the electric field oriented like that, this configuration has lower potential energy than when the molecule is like that and the electric field is oriented like that. Right? You can think of it this way. The molecule tends to align with the electric field. So if there's a thermal vibration affecting this one, it will tend to just align this way, so it has more potential energy. So this is a higher state of energy than this one. So now what we have to do to consider the oscillating fields is by simply using this equation and changing those electric fields with the time averaged electric fields, because the time frame of those responses, well, the typical response time of those processes are much longer than the frequencies of the optical fields, right? So I can write it directly. Yeah, so this is basically just what we can do. Just write it down. So U is equal to minus 1/2 of E, square minus 1/2 E, square cosine. And then if I want to have if I want to retrieve, yeah, so we keep that in mind, and then what we wanted to do is to calculate the refractive index. So recalculating the refractive index is given by, the expression is given by n square is equal to epsilon is equal to 1 plus chi is equal to 1 plus n times alpha. So alpha here, rather the average value of alpha, denotes the mean polarizability experienced yeah, so mean polarizability. In general, for an optical field, the energy contained in the optical field is given by minus the energy related to the polarizability from an optical field is given by this. Comma here. And so also I can write down that alpha is given by, this is just taking the average value of the general expression of alpha, so cosine square of theta plus sine square of theta, and so this is simply given by and again, all those average values represent what's going on. It represents a thermal equilibrium, right? So we need to consider the thermal effects due to the law of Boltzmann, right? So the cosine, the average value of the cosine is not obvious. This is some integral over some solid angle. Cosine theta exponential of minus u of theta. Oh, we have u. Okay, very good. Divided by kt and divided by some kind of normalization factor minus u. Yep. So this is somewhat familiar, right? This is the Boltzmann distribution. You've seen that before. So omega is explicitly given by 2 pi sine of theta d theta, and a is given by wait, I haven't talked about a. I will introduce a as alpha parallel minus alpha perpendicular e square averaged kt. Now it seems that like I'm changing notation, so I'll just try to be okay. So the refractive index, from these expressions, I can find what the refractive index is when there's no field, and we'll use this value later. So to do that, it basically means that A, when there is no field is equal to 0. Oh yeah, I can rewrite this in terms of A before I talk about this. I will rewrite the integral with the A in it, which is a bit more handy. That's why the A is appearing. So 0, 0, from 0 to pi cosine square of theta exponential of A cosine square of theta sine of theta d theta. So this is just an alternative way of writing the integral. And then I say the case where A is equal to 0, so when there's no field, I will find that, and this is something that you can try at home or during the weekend when you're feeling bad, I guess. You want to solve integrals, stuff that people have done in the 19th century. So you will find that it is equal to 1/3. Yep, 1/3. Find this relation, and by previous equations that we had earlier, you will have that this is equal to this. We just derived that. Very good. Okay. And we find from this equation we can retrieve the refractive index that would be equal to n naught squared is equal to 1 plus this. So when you consider that there is when there is an applied field, so when A is not equal to 0, there will be a different refractive index arising from the different value of alpha. So you find that n square, so I will write A is not equal to 0. A is not equal to 0, you will have that n square is equal to 1 plus n alpha this perpendicular plus alpha parallel minus alpha perpendicular, and then you have the cosine, the integral that we've been talking about earlier on. And now if you want to have the change in the refractive index, you will find that this is simply it's really just a factor that will be depending linear with the cosine square that we had that we can calculate with a certain value of A. So we find that the change in the refractive index delta n, or rather n is equal to n naught plus a change in the refractive index, and the change in the refractive index is equal to n over 2n naught alpha parallel minus alpha perpendicular cosine square of theta minus 1/3. Yeah, which is the result that corresponds to n naught. So this is not an easy integral, and it is tabulated all over the place. And you can find that you can find in a certain book about nonlinear optics a plot of this integral depending on the value A. Just pick up your favorite book about nonlinear optics, and I will be erasing this. I know what is your favorite book about nonlinear optics, so I'm sure there's the plot in it. You will find that this cosine square of theta minus 1/3 versus A, and now let's put that 2, 4, 6, 8, 10, 12, and just have this kind of scaling. You will find that this is going like that. Wonderful. We see that in this region, the increase of the dn, the change in the refractive index, grows linearly with A, and A, as we know, is proportional to the intensity of the field, or the average time-averaged electric field squared. All right. So when you slowly increase, you have this. Let's just remind us what we're talking about. Sometimes it's useful. We're still talking about a bunch of molecules shaped like that, and I apply an electric field to that. And so when I send an oscillating field into this liquid, and I increase the power of this field, I will see that there is a change in the refractive index that is first going linearly with the power of the field, and with the intensity of the light field, and then it will reach an asymptotic trend when some kind of saturation, or rather it's not saturation, it's just they will just be aligned. You pump them so much that they just get aligned and just stay there, basically. So there's no counter effect due to thermal effects anymore, just because you have such a strong average electric field. Okay. Yeah, so it is found that this is a numerical, or rather this is just tabulated values that have been plotted, but you can find that you can do a term-by-term expansion and find that this guy expanded in A will be varying like that. So 1/3, this is the term that we had before, plus 4A over 45 plus 8A square 1945 plus dot dot dot. So plus other terms. And now it seems that we are approaching something that we've seen before. We're going there. So we find that we can have an expression that corresponds only to those two terms, and this expression for the change in the refractive index will be 4, no wait, there's no 4 pi here, that will be n over 2 n naught alpha parallel minus alpha perpendicular for A over 45. Wonderful. Wonderful. So expanding this, or rather explicitly writing this in terms of the practical variable that we use in the everyday life, I can write it this way. Square. This is E square divided by KT. Great. Great. And so I find that I can define a N2 in terms of the polarizability of the molecule. Yeah, again. Okay, where N2 bar is given by this, well, all the prefactor to the average time varying electric field. And so in the same way, you can, from this value of N2, you can use the principles that I used at the beginning to extract the chi3. So this is why I was not finding the chi3 earlier. I was not finding the chi3 later on in the notes because we were stopping there. So I have the change in the refractive index, and from the change in the refractive index, you can extract the chi3. Wonderful. Now we're going somewhere. Or not. No, but I'm not sure. I'm not sure if I'm continuing actually. So now you're praying that I will stop now, and I think I will just stop now. So the other parts of the chapter that will or should be covered are the electrostriction that I mentioned earlier. We just did the molecular orientation effect. Electrostriction. There is saturable absorption that I was maybe supposed to cover, photorefractive effect, and then the non-resonant electronic polarization. So those are other parts of the chapter 4. But yeah, I think it's enough for today. And I think Bob will give this material much better than I will. Are there questions? So maybe I can just summarize this part. So what we have done is we have taken the properties of such a molecule, an organic molecule that has a cigar shape. In this case, it had a cigar shape such that there was those two elements of the polarizability. But any other molecule, organic molecule, could have other elements in this polarizability tensor. And when there is other elements in the polarizability tensor, of course it will change everything. So the way we solve this integral will be different, and many other properties will be different. So we used this type of molecule as an example to go through this process, and at the end give some kind of flavor of what's going on. For details about like this interplay between thermal effects, thermal statistics, and such, I invite you to read more in the book and ask questions to the boss. But otherwise, I hope I gave you enough flavor of what kind of effects we're talking about. Questions?
Just I want to ask about the midterm, because I think this is last lecture, because next Monday is start reading week.
I have no information about the midterm.
No, but because I want to ask about we start to prepare for midterm from chapter 1 until here, or the whole?
Well, when I did the course, the midterm was about chapter 1, 2, 3, and I think that was it. I think it was 1, 2, 3, but that was, and maybe the first part of chapter 4 also, like the first thing I talked about, right?
Yeah.
You know, when I told you, hey, look, there's a intensity-dependent refractive index.
Mm-hmm.
There are some implications in terms of the phase. You know, I told you that. So if you have a different refractive index, it means that there will be some kind of retardation in the medium. So can you express what is this phase shift due to the nonlinear refractive index? Right? So this is the kind of basic questions in nonlinear optics that you should be able to answer. And wink, wink. This is the kind of question that should appear in the midterm. Otherwise, I think Bob is giving some. Is he giving some kind of test exams or not?
He wanted to do it.
But
Okay. Well, if he wanted to do it and did not do it, there is a good chance that he just forgot because he's such a busy man. So why don't one of you write to him and ask, hey, is there a how do you call that, like practice exam kind of, or a previous exam that we can look at, right? And again, wink wink, the kind of questions often are very similar. And so if you think it's a very intensive, this derivation of the chi3 using the quantum mechanics, well, this is the kind of stuff that might appear in the midterm.
That's too long.
Yes.
No comment.
Well, I have no details whatsoever. I mean, I'm not even the TA for this class because the TA, it turns out, is also in Rochester right now. So I was asked last week for that.
That's early.
And at this point, you can leave. It's all right.
Yeah.
It's done.